So in this video, we are trying to understand PCA in a very minimal level by using R. Okay, so we are not going to use much of any complicated plots or anything. So just using iris data, how we can actually use this or apply this PCA upon it. So you are using the head of just to understand how our data is. This we have already seen. So we have 5 different attributes, and it has, so it just prints the all the first 5 or 6 observations from the data. And now you are going to create a new data frame. So in this new data frame, what you are going to do is that you have iris, you are taking the iris and you are taking 1 to 4. That means you are going to take sepal length, sepal width and till petal width. You are not going to take species. Okay, you are going to exclude this particular data. Okay, and you are going to print this. So when you print this, so when you print this, you could see the data being printed as only 4. Okay, so we have got just the 4 different attributes which are taken. So that is what is seen here. Now say you could try this particular function. So I just wanted to tell you by this example that there is 2 different functions. One is actually print comp. Okay, so I'm just trying to use this principal component. Okay, print comp. So here this is the data frame. This is the function print comp. So this is the function print comp, and you are taking the data frame D and you are making the correlation as true and the score as true. So this is what you are basically taking, and you are trying to run it, and now you are going to take the summary. That means you would have already got the principal components. So you will get the component 1, 2, 3, 4, and it will simply give you the standard deviation, proportion and the cumulative proportion. These are the 3 things which will be given to you. And the standard deviation just says that, so understand, initially itself understand component 1, component 2, component 3, component 4 actually gathers most of the useful data, and component 1 will have the most useful data gathered from your original data set, and component 2 will have the second most useful data which is gathered from the whole data set. It goes like that, goes on like that. So when you take your component 1, okay, the standard deviation is 1.7, the spread is more, and when you take your component 2, this is the spread, and it just goes on like that. Now proportion of variance will clearly give you how much from your data will be able to, how much from your data is actually explained by component 1. That means here when you look at this particular data, it says that 73, almost 72.9 is almost 73% of your whole of the original data, whole of the data from original data set can be explained by using the component 1. So this shows that this value, this proportion of variance for the component 2, that is 22.8 or 23, says that almost 23% of the data could be explained by component 2, and so on and so forth. So this is how it, you have to interpret your data and your values which you get. And now the third one is basically cumulative proportion. So in cumulative proportion, basically what happens is that, say for the first one it is just 72.9 or 73%, and if you are considering both, say you are going to reduce your data set from 4 dimensions to 2 dimensions, that means you are going to consider only component 1 and component 2. So in such case, the cumulative proportion is almost 95. That means 95.8 or 96% of your whole data could be explained if you are considering both component 1 and component 2. 99.4 or 5% of the data could be explained by if you are considering all the 3 and almost completely everything. So it's like exactly like you're taking the original data set when you are taking all the 4 components. This is how it is actually interpreted. So now if you want to plot, okay, this is the simplest plot ever you could see. So when you simply plot it, it will simply give you, okay, the proportion upon the variance. So this is actually shown upon the variance. So 73%, then comes here 22%. So it just shows you like, how the data has been, plotted based on variance. Okay. Now if you want to see, which all are the data or which all are the components that has to be taken, then you could use this elbow method. So this plot gives you your elbow method. So that shows you very clearly. So you can take component 1 and component 2 and maximum component 3, because then after that there is no use at all, because component 3 and component 4 is almost kind of similar. So if you take this two components itself, you will be able to give a maximum information from the data. So this elbow method will help you to identify. So it looks like an elbow. That's how. So when we keep our elbow, how our elbow looks, that is exactly how this is actually taken. So this is the elbow point. So from elbow point we will not take. So we will take all the points before the elbow. So that is what basically it does. And then if you are doing a Y plot, so all this we have already seen before. So you could see this. So when you zoom this, one second. Okay, I don't know, it is already. Yeah. So when you zoom this, you could very clearly understand, how your data has been spread across component 1 and component 2. So in the component 1, you could see that, there is a higher concentration of sepal length, petal width and the petal length, and the sepal width is actually least taken. But in the case of component 2, sepal width is more taken and this, in the lesser way. So this kind of an interpretation could be understood by this biplot. Okay. Now the next one is, dimension of D. So your dimension of D is 4 basically, and you have got 150 observations. And if you want to see the attributes of attributes of PC, so these are the attributes which you could use in your principal component. So you can get a standard deviation, you can get the loadings, you can get center. This is for your principal components, and you can have scale, and you can have scores, you can have the number of the observations, you can have the call. So these are the various things which are available in your print comp. Okay, in your print comp function for the principal components. So if you understand that, okay, if you want to see, okay, what happens in loading, you can basically use this particular function. Okay, you can basically use this function. So this PC dollar loadings, if you try this, it just clearly gives you, okay, for each component, how the loading has been. So 4 loadings, okay, how the proportion has been. So the standard deviation, the proportion variance, so how it is actually distributed, you could see that here. So when you see this for the principal component 2, okay, you could see that, they have not actually considered this petal length and the petal width at all. So that is what you could understand. So you'll be able to understand, a clear understanding about how this principal components has been formed from the original data, and from the attributes, what are the attributes which has been actually taken, that could be understood by this particular data. And now the next one is actually, yes, the scores, of course. Okay, so if you try using the scores and see, these are the scores. So you could very clearly understand how the data has been, and what all are the scores of the each and every component, okay, which you have. So for all the 150 observations, what all are the scores which is actually calculated, that could be understood by this particular thing. So this is nothing but your vectors which is formed. So this eigenvector, so you could very clearly understand, what are the scores which has been formed for each and every observation. So all this information could be understood by using this particular example. So this is all about, this is a simple PCA. This is like, there is two different things. One is actually your print comp. Okay, print comp is one of the function which is there, and the other function which you will be seeing is nothing but PR comp. So these are the two different functions which are available in R for you to work and play with. Okay, so please try doing this and try to understand how your data will look like, and how you can actually try to change the values here and try to change what is the difference that you're going to get. So make your correlation false and make your score as false. So what will happen, so you can just trial and error all this and try how everything works. So hope you understood this. So thank you so much. Hi, hope you're all fine. So in this video we are just going to see about principal component analysis using RStudio. Okay, so hope you all know about principal component analysis. So principal component analysis is a dimensionality reduction technique which is possible and which is helpful for you to find out the various patterns, and it also helps you to identify the most related or codependent attributes. So if few of your attributes are really codependent, then you can decide upon whether you need both attributes there, whether they are positively related or whether they are negatively related, so all those stuff. And one more thing is that in principal component analysis, like principal component analysis, there are so many different ways, but in principal component analysis, basically you take the data, you collect the data, then you do the standardization process or the normalization process. And once you have done that, you have to find out the covariance metrics. And from the covariance metrics, you will find the eigenvectors and the eigenvalues. And once it is done, then you are ready to come out with your reduced matrix. So this is how the dimensionality reduction basically happens. Say if you have a 5-dimensional data, then you will have 5 principal components which you get from the PCA. And the first principal component will try to capture as much as information as possible from your data, and the second principal component will have the second most useful data, and third principal component will have the third most. So it just goes like that. So using the elbow method or the different methods which are available, you can actually select whether you can reduce your whole attributes into 2 principal components or not. So this principal components basically comprises, it's not like exactly you have 5 attributes, you are just reducing it into 2. It's not like that. So this principal components are basically kind of data which is captured from all the attributes. So that is how it is. So we will see more about it in this video by doing a little bit of coding. Okay, so here we are going to take the iris data set, and I have actually taken captured all the the commands and kept it ready so that it is easier for you. So first of all, we are just trying to understand what our data is. So this is we are going to take the iris data set, okay, and we are just going to print the first 5 data. So that's nothing but your head data. So you know already about all this. We have already seen this in so many different classes. So we have sepal length, sepal width, petal width, everything, and the species. So these are the various attributes which you could see in your data. Say if you are just printing iris, okay, str will simply give you the structure. So you will get a complete understanding about your data by this. So there are 5 different variables and 150 observations. So so all this information will be provided to you by the structure. Now so if you want to get the complete summary, the 5-point summary of how your data basically has been spread, so you could use this. So you will have the minimum, the maximum, and then the first quadrant, the median, the mean, everything is given here, and the species, and each of the species contain 50-50 observations. So that's how your whole data set is about 150 observations. So all this information could be understood by using the 5-point, by taking the 5-point summary. Now we are going to perform the PCA. Okay, so while performing the PCA in R, the most beautiful thing which we could see in R is that the functions are so simple, right? So we are going to use the PRComp. This PRComp is nothing but the principal component analysis, and we are going to do the principal component analysis upon the iris data. And in that we are going to discard the last one. Okay, we are going to discard the last one, or we could also say that we are going to take the first 1 to 4. So either ways it is correct basically. So either way you could do. So either you could select the last one, or you could actually say that 1:4. So that just takes that we are going to compute the principal component analysis upon the sepal length, sepal width, petal length, petal width, and discarding the species. We are not going to take this. So this is what it means. And this is actually, we are actually putting into a data frame, say D. So D is the data frame for this particular process. Okay, so when we run this, okay, so all good. So now what you have to do is that, say if you want to say now we have actually taken all the 4, right? So I just wanted to show you this as well. Say if you want to specifically select, okay, specifically select a certain for the principal component analysis, you don't have to take, you are not interested in taking all the attributes, then you could basically take, say, if you want to take only sepal length and petal width, this is also possible. So by this, basically you will be computing the PCA just for these two by taking the data from iris for sepal length and petal width. So this is also possible. So I'm just putting it here so that it is helpful for you later. So this is basically for you to understand, okay, a specific attribute. So this is for PCA for specific attributes. Okay, and so this is how you will be doing it. And now moving over to the next step. Okay, so can we just try plotting this and see how will it look like? Okay, so that is what we have to see next. So when we are plotting it, see, this is the scaling function which we have. So we will demonstrate the scale function. Before that, we will simply demonstrate how our data basically looks like here. So once you see this, you could see this is actually the plot for sepal length and sepal width. Okay, so you could see that how our data is basically distributed. Okay, now in order to help you to understand the difference between scaling and the normal plot, okay, we will try to plot the scaled one. So for scaling, this is the function which you have to use. Okay, for scaling you have to use this particular function. One second, I'll just make it up. So see, so this is the function. So scale is the function which you will use for scaling the data. Okay, so you will get you are taking the same attributes sepal length, and you are also taking the same attribute sepal width, and you are scaling each of the data and trying to plot it. Okay, so we will see how it will look like. So once scaled, you could understand that, okay, this is the data which you have got. Okay, so we cannot see any basic difference in the data that is actually spread, or how the data is basically spread. So when you see, I will take the previous plot. This is the previous plot, and this is the plot now which we have got. This is the scaled one, okay, and this is the previous plot. So when you see these two plots, the only difference where you could find is in the values, right? So here the values basically ranges from 4.5 to 8, and here the values basically ranges from 2 to 4. Okay, but when you see the scaled data, you could see that the values is between like -2 to 2 and -2 to 2 on both the axes, right? So it's like you have your, so as you have already seen in PCA during our class sessions, right? So we have our data. When we scale the data, its direction does not change. Okay, we are not changing its direction. The data is exactly as such. Okay, but we are just positioning it to a within a new scale or within a new range. That is what is happening by this scaling. So hope you understood that. Okay, now moving over to the next one. So one second. So what we are going to do is that, okay, so I'm just going to run this, okay, and I'm going to plot D. Okay, so now you could see here, so this is the this is one particular function scale where you could actually do lot of homework. Okay, so here normally the scale will be false, so here we have actually taken the scale as true. Okay, so now we have taken all the attributes from sepal length to petal width, all the 4 different attributes excluding the last one, that is species. Okay, and we have actually made the scale is equal to true. Now you have actually calculated the principal component analysis upon that particular value, and you are putting it into a data frame and you are printing it. Okay, so once you are printing it, these are the details which you are getting. Okay, so you could see that there is a standard deviation of 1.7 for the first attribute, second attribute, this is the third attribute. So this clearly helps you to understand how your data is basically spread. Okay, now and here when you see, you could also see, okay, the PC1, the PC2, PC3. So always understand, if you are using 4 attributes, that means that you are working with 4 dimensions. So if you are working with 4 dimensions, you will have 4 principal components. Okay, so that is why you are getting PC1, PC2, PC3, PC4. So how many components we need to take further is up to us, and we have different methods to decide upon it. That's what I have already told you. Okay, so in this particular thing, when you look at it, okay, this is PC1. Okay, so PC1 gets the value. So what is the kind of the value that has been, the percentage that has been taken from sepal length, okay, and sepal width, okay, petal length, petal width. That is what actually is shown here in this particular PC1. And in PC2, what is the percentage of the values that has been taken in PC3, PC4? So this is how it is actually taken. So by seeing this, you will be able to clearly understand, okay, what is the proportion of the values that has contributed to PC1, PC2, etc. Okay, so hope you understood this. And then if you are simply printing the summary, okay, the summary will give you the complete understanding about the data, more understanding about the data. So it's like you get the spread of the data or the dispersion of the data by using the standard deviation. Okay, so you could see that the maximum spread is actually, or the dispersion has happened in the PC1. Okay, so it has gathered almost a lot of information basically, and this proportion of variance basically gives you. So these are the three different values which you will get in summary D. So just to have more more insights over to these two, when you plot D, okay, when you print D and when you print the summary of D, just to give you more insights. So here you could see that for the sepal length, okay, for it has been printed for PC1, PC2, PC3, PC4. So when you see this, these are nothing but the eigenvectors. Okay, so the eigenvectors of the which will be used for the calculation of the linear transformation. So it's like, say if you have the sepal length of 3 and the original value 3, and say for sepal width is 4, and say for petal width is say 5, and this is 6. So say these are the values. So basically 2 into 2 multiplied by this particular value, plus 3 multiplied by this value, plus 4 multiplied by this value, 6 multiplied by this value. So this is kind of the calculation which will happen internally. So so just to understand that, these are the eigenvectors which has been calculated in terms of your, during the principal component analysis, you need to do the linear transformation. So that is what basically you're doing. So these are the eigenvectors. Okay, now just to give you more insight, so as I told you, so this shows you the spread of the data. So that means that in PC1 basically, so whenever somebody says about PC1, so that is the first principal component which has got maximum in useful information that has been incorporated, and PC2 contains second most useful information, PC3 contains third most, and PC4 fourth most. This is how it goes. And if you have 4 dimensions, basically you will have 4 different principal components. And this proportion of variance just says that, so from the whole data, 73% of information has been explained by PC1, and 22 or 23%, almost 23% of the information from your data has been explained by PC2, and 3.6 or 3.7 percentage of the whole data has been explained by PC3, and PC4 is able to incorporate only very less information, that is 0.05. So that is what you have to understand by this proportion of variance. And there is something called cumulative proportion. So this cumulative proportion just clearly explains you, by PC1 you get 73% of the data, and if you're including both PC1 and PC2, as say if you're say if you have 4 dimensions and you're going to reduce it into 2 dimensions, and if you're going to include both PC1 and PC2, then you will get a cumulative variance of 95. That means if you include both PC1 and PC2, you will get 95.8. So almost 96% of the useful information from the data, or 96% of the information has been included or explained by this PC1 and PC2. And if you are using PC3, say this cumulative proportion, it gives you an information that, so by using PC1, PC2, say if you are actually reducing it into 4 dimension to a 3 dimension, okay, then you will get almost 99% of the data will be explained. and if you're using all the 4, it's exactly like, the complete data set has been utilized. So this is how you have to understand about these are the explanation which we get from the explanation of the principal components. So hope you are able to understand that. Now the next one is nothing but we could try plotting it, okay, because if we are able to plot it and if we are able to understand it, then it is easier for us to understand how everything works, okay. So now here now this plot basically just gives you an information. So I told you, like, say for 4 dimensions you will have 4 principal component analysis, sorry, 4 principal components, or some people will also say that it is, so 5 dimensions were there, so you will get 4. So okay, n minus 1. So here it is actually 4 dimensions of 4 principal components we are getting. So how many principal components we need to take? So this you have already seen, okay, before. This is nothing but your elbow method, okay, which we have already seen before in the clustering technique in order to identify the number of the k that has to be taken. So in this particular example, it is very clear that from 3 there is no major difference. So basically if you take these 2 components, then it will be able to provide you a better representation of your data by using, so with the help of 2 dimensions you will be able to get maximum data covered. So this is what is we use it by using the elbow method, and this L is nothing but the linear. So this method is basically nothing but the elbow method in order to understand the number of principal components that you have to take or that you have to choose. Now the next one is, there is another way of doing it, that is nothing but the biplot, okay. So this biplot basically makes your data okay, this is, I'm just going to zoom this so you'll be able to understand the data better. So this biplot basically help you to understand your data. One second. Say if you give here, if you give str of d, okay, str of d, so you will be able to understand all this. Say if we zoom this, so you could see how the data is basically spread. So you have your PC1 and PC2, okay, and how for the PC1 and PC2 the data has been spread. So in PC1, so when you draw a line, you could understand that PC1 mainly incorporates petal length, petal width and sepal length, and it has got few of the sepal width, okay. That is what you are able to understand by seeing this particular data. And if you see PC2, it has got more concentration from sepal width than the other data. So this is what you have to understand by using this plot data, okay. So this is nothing but your biplot. And then if you are actually giving the str of d, so as we have already seen, it gives you a lot of information about the standard deviation, about the rotation, then center, the scale. So in that we are trying to explore more about the scale and the x. So this x is nothing but the PC1s. So okay, this just gives you the values of the various PC1, PC2, PC3, PC4. Okay, so this is how, if you do an structure of the D now, you will be getting something like this. Now if you want to compare and see, say no, by seeing this particular diagram I am unable to understand or clearly understand how much from the original data set, okay, how much this principal components has been used. I want to compare with the original data set this principal components. If you want to do that, there is a function called cbind, okay. There is a function called cbind which helps you to bind your data with the original data. So here this is your original data which is provided, okay, and then you are actually from the D is your data frame, D is a data frame which you have actually generated here, and from that you are actually taking X. So X is nothing but X gives you the principal components, all the 4 principal components. In that you are taking 2 principal components, okay. So you are taking 2 different principal components. So when you plot it, okay, you can simply take the head so that you will get to know about the values. So when you take the head of iris 2, you could see here So the values has been given. So all the 4 different values from the iris, all the 5 different values from the, this is your original data set. See, this is your original data set, sorry. So this is your original data set. So you have species, you have petal length, petal width, sepal length, all the original data. Along with that, you are taking x12. That means in your x, you have 4 different values. In your x, you have 1, 2, 3, 4, 4 different values. In that, you are taking 1 to 2. You are taking 1 to 2. Okay, that means you are considering PC1 and PC2 values. Okay, so this gives you an understanding about what is your value for each and every attribute and what is the value that you have got in PC1 and PC2. So whether you have a positive values which you have got, or you have got a negative value, or whether you have got a positive value for the PC1. So each one, so how the data has been incorporated in PC1 from the original data in PC1 and PC2, that could be understood by this particular thing. So in order to understand more, okay, with a pictorial representation, okay, what you could do is you could try installing this ggplot2. I think this we have already used before for the clustering. Okay, we have already used this. So you can use this, yeah, this is already loaded package. So it will just take the, it will load it, that's all, and it is just loading. Then what you could do is you could just load it into the memory. Okay, so that's why we are using this library of ggplot2. Okay, it will simply load it into the memory, so everything is fine. Okay, now what you have to do is, one second. So now in order to show you how it is to be done, so we have a function. Okay, so we are using this ggplot. Okay, what I will do is I will take you through this. So for the ggplot, okay, so here the package name is ggplot2, but here the function name is ggplot. Okay, and you are taking your iris2 and the aesthetic function, the PC1 and PC2 we are going to plot, and we want, basically we cannot see it in terms of species, but here we need to understand with related to species column or attribute, okay, how PC1 and PC2 has been given, okay, or has been computed. So that is what we need to understand. So we are taking this particular label. So normally we don't use this label, but here we explicitly want to understand how PC1 and PC2 has been calculated in terms of the attribute species, and we are using this function fill species. So this is just to plot, okay, plot the PC1 and PC2, okay, and we want it in terms of species. That is what we have given there. Now the second part of it is basically we are using a function called statistics underscore basically ellipse. So it has got various attributes available. You could see that. Okay, in that we are giving only certain attributes. So here we are giving geometry. So we need to be drawn in the form of a polygon, and the color has to be black. Okay, the color has to be black and the alpha has to be 0.25. So this is the second part of the this particular function. So stat, okay, ellipse, geometry, geom is nothing but polygon, and color and alpha. And there is third one. So how are you going, how do you want your points to be? Okay, so that is what is shown here. That is the third part. So in geometric point, okay, in geometric point you can clearly give the shape and the color and everything. So the shape is 21 and the color is given as black. So when you try to run this, okay, you will be able to see this particular plot. Okay, so here at the side you could see it is actually printed based, or it is actually plotted based on the species. So setosa, versicolor, virginica. So 3 different colors has been used for 3 different species. Okay, so when you zoom this, okay, when you zoom this, you will be able to understand it clearly. So there are some outliers for everything. So there are certain outliers which you could see, sorry, which you could see, and how PC1 and PC2 has utilized these 3 different species that could be seen here. So in your PC1, if you say you have an overlapping of your, so that means the values for versicolor and virginica, there is some similarity between the values. Okay, so there is more relation or dependency. And when it comes to Setosa, it is having a lesser what is that, it has incorporated only very less. Okay, and but when it comes to PC2, it has incorporated more of Setosa, and these values are lesser. So all this information you will be able to understand in terms of the species. So species is basically the categorical values here. So with that you will be able to understand here in a better way. So these plots, this GG plot will clearly help you to understand how the data has been basically how the data is actually explained in the principal components. So that is very clearly explained here. Now we have a simple thing to do. It is nothing but the correlation. Okay, say if you want to understand the correlation between the various components, okay, then what you could do is, so here we are taking all the 4. Okay, so that means we are just excluding the species alone. We are taking the IRIS data set, we are excluding everything. Okay, and we are also comparing it with the IRIS data, IRIS2. IRIS2 means this is our original, the new one which we have got. So when you do this, you will get this particular correlation between your PC1 and PC2 with all the 4 columns which is there in your original IRIS data set. So PC1 is basically 89. Okay, that means it has got a positive. So it has actually included, or it has got a positive. So that means in the PC1 the sepal length has been included. 89% of sepal length has been included. So that means more more of sepal, the values from the sepal length has been included. What about the sepal width? Okay, it is very less. So here there is a positive correlation, and here there is a positive, very positive and a strong correlation. Okay, and while contributing to your PC1. So PC1 basically have taken sepal length, petal length and petal width data, and very less of sepal width data. So this kind of information you will be able to understand if you try to utilize this particular correlation function. In the case of PC2, you have got only very less. It's all negatively correlated. So when we take PC1 itself, we will be able to understand it has incorporated almost all the useful information from the whole data set. So that is what we are able to understand from this. So this is actually a representation for your PCA. So basically in R, okay, when you are using R, the main thing which you have to keep in mind is that the function which you use is prcomp. Okay, so prcomp is the function which you could use in R. Okay, and there are different type of plots available. Then the other major thing which you have to understand is the scaling function. So the scaling function is very important in PCA, because you are basically scaling your data from higher dimensional to a lower dimensional space. So you are basically performing a dimensionality reduction by using PCA. So this is very, very important. So you can just make your hands dirty by changing the values of scaling, and then by using the ggplot you will be able to understand how, and from the original data set how much it is contributed to the PC1, or in the new data set, okay, how much it has taken from the PC1, so how the PC1 is calculated. So everything, what all are the eigenvectors, all those information you will be able to understand by using this particular functions. So hope you got a bit about how the PCA works in R Studio. So please try this out, and let's see how it goes. And if you have any questions, you can always ask.